1 minute ago, high on the upper southeast flank of Mount Etna, the mountain quietly tore itself open. A new fracture almost 100 feet from end to end split through frozen lava, near 10,000 feet wide enough for a car to disappear inside. There was no eruption, no roaring column of ash, no earthquake rattling the cities below, just a raw black wound cutting downslope. When geologists overlaid its position on their maps, the room went silent. The crack falls almost exactly along the same ancient slip surfaces tied to a collapse 200 years ago, the one that drove a tsunami into these coasts. If Etna is tracing that line again, is this the first stroke of its next plunge into the sea? From a distance, Mount Etna looks solid and eternal, a dark pyramid rising above the lights of Catania and the fishing towns along the Ionian coast. Lava flows from past eruptions have frozen into black ribs on its slopes. Villages cling to those ribs, their streets paved with basalt blocks cut from old eruptions. Tourists buy postcards, locals park their cars under terraces that look straight up at the summit. It feels like the mountain has always been there and always will be. But the closer you get to Etna's southeastern flank, the more that illusion falls apart. Here, the volcano is not resting on hard, unshakable bedrock. Beneath the lava and ash lies a deep pile of ancient marine sediments, layers of mud, sand, and clay laid down when this part of Sicily was seabed. Those layers are soft, weak, and soaked with water. Instead of a steel frame, Etna's southeastern side sits on something closer to a saturated sponge. When you place a mountain more than 3 kilometers high on top of that, gravity never really lets go. For years, geologists assumed that any movement of this flank was driven mainly by magma pressure from within, that the volcano pushed its own sides outward during eruptions and then relaxed as pressure dropped. Instruments did show slow motion creep toward the sea, measured in millimeters per year. Cracks in roads and terraces could be blamed on normal tectonic stretching or on the expansion and contraction that comes with eruptions and cooling lava. The idea that the entire flank might be sliding as one giant block on weak sediments below was considered but not taken as the dominant factor. Then they started looking offshore. High-resolution seafloor mapping revealed chaotic piles of boulders and broken lava far out on the submarine slope, arranged like a frozen avalanche. Cores drilled into the seabed, pulled up disturbed layers of sand and clay jumbled and mixed as if something enormous had plowed through them. When these deposits were dated, they pointed back to a period thousands of years ago when a huge chunk of Etna's eastern side appears to have collapsed and plunged into the Ionian Sea. On land, the vast amphitheater of the Valle del Bove, a 5-kilometer-wide gouge on Etna's flank, lines up with that offshore debris like a scar with its missing flesh. Step by step, a disturbing picture emerged. Etna's southeastern flank is not just cracked. It sits on a basal shear zone, a broad, weak horizon where soft sediments and lubricating fluids act as a sliding surface under the volcano's own weight. Above that surface, lava flows, cinder cones, towns, and forests all move together, creeping downslope like a single gigantic landslide. Most of the time, that movement is so slow no one notices. But if the weak layer fails more abruptly, history suggests the result is not just a reshaped mountain. It is a wall of displaced rock capable of pushing up waves that race outward faster than any warning siren. Today, the same coastline where fishermen mend nets and children play on black sand beaches lies directly in the path of that potential motion. GPS stations, tilt meters, and underwater instruments dot the mountain and the seabed, quietly tracking every millimeter of drift toward the sea. From above, Etna still looks majestic and immovable. From below, the data tells a different story. Its southeastern side is already on the move. The fracture that just opened near the summit is only the most visible crack in a system that has been sliding in slow motion for years. The real question is whether that motion will stay slow. If Etna's southeastern flank were only drifting a few millimeters a year, this could be written off as the slow settling of a huge pile of rock. But the measurements tell a sharper story. Over the past decades, GPS stations anchored into the lava flows have shown that parts of the flank are sliding seaward at centimeters per year and not always smoothly. Sometimes the motion speeds up, then eases again like a heavy object inching toward the edge of a table. The real shock came when scientists extended their instruments offshore. Arrays of acoustic transponders were placed on the submarine slope, connected by precise distance measurements through the water. For months, the network sat quiet, recording tiny continuous changes as the flank crept seaward. Then over the course of just 8 days, the system detected a sudden jump roughly 4 centimeters of downslope movement along the underwater part of the flank. There was no eruption on land, no major earthquake, no obvious trigger that people in the villages could feel. The mountain had simply lurched forward underwater silently. That single quiet jolt overturned an old assumption. If magma pressure inside the volcano were the main driver, the biggest movements should coincide with eruptions or strong seismic swarms. Instead, the data showed that gravity acting on a weak base can by itself produce rapid shifts. In other words, Etna's southeastern side is not just flexing in response to what happens in its magma chambers. It is being pulled constantly and relentlessly toward the sea, and the weak sediments beneath it are capable of letting it slip in discrete, unsettling steps. This matters because we have seen what a large-scale collapse can do. Geological and marine evidence point to a massive flank failure thousands of years ago when a huge slice of Etna's eastern side broke away and thundered into the Ionian Sea. The resulting debris avalanche left a chaotic field of boulders on the seabed and likely drove a tsunami toward the surrounding coasts. Modern simulations of similar collapses suggest waves tens of meters high racing outward, reaching nearby shorelines in minutes, not hours. Towns that today host beach promenades, ports, and apartment blocks lie exactly where those modeled waves would hit first. The frightening part is not that such a catastrophic collapse is guaranteed or that it is imminent. It is that the mechanism exists and is already active. The same sliding surface that allows the flank to move 4 centimeters in a week without any obvious warning could, under the right combination of triggers, an offshore earthquake, an intense intrusion of magma, prolonged heavy rain saturating the sediments, fail on a much larger scale. There may be no dramatic buildup visible to the naked eye, no towering eruption column announcing the danger. The first unmistakable sign for many people along the coast could be the sea pulling back suddenly, or a wall of water appearing on the horizon. Etna's flank does not have to race downslope all at once to be dangerous. Even smaller partial collapses could generate destructive local tsunamis, damage infrastructure, and reshape the coast. The fact that the system is already moving, already capable of sudden silent shifts, is what keeps scientists and civil protection officials awake at night. A volcano that explodes loudly gives people something to react to. A mountain that fails quietly from the bottom up gives far less time. To understand what is happening to Etna's southeastern flank, you have to leave the postcard view of the volcano and drop down into the numbers. Across the mountain, a dense web of instruments is bolted into lava flows buried in soils and anchored to the seafloor. Each one measures a tiny piece of motion pressure or tilt. Put together, they reveal a vast structure that is not fixed in place but slowly sliding. On land, the most important tools are GPS stations and tilt meters. Steel poles are drilled deep into old lava flows and topped with GPS antennas that talk to satellites overhead. By tracking the position of each antenna, scientists can see how the surface of the volcano moves over time. We usually think of GPS as something that can tell us where we are within a few meters. These stations are more precise. Over weeks and months, they can detect shifts of just a few millimeters. On Etna's southeastern flank, many of those stations show the same pattern, a steady drift downslope toward the Ionian Sea. Tilt meters add detail. These are extremely sensitive levels cemented into the rock, able to measure when the ground tilts by a fraction of a degree. They pick up subtle changes as magma moves under the summit, but they also track broader flexing as the flank slides. When the southeastern side of the volcano creeps, whole clusters of tilt meters lean in the same direction, like tiny compasses pointing downhill. Combined with GPS, they show that the motion is not just local cracking. Large sections of the flank are moving together like a single block, gliding on a hidden surface. Beneath the sea, a different kind of network watches the submerged continuation of that block. Arrays of acoustic transponders sit on the seabed, paired with receivers that measure how long it takes sound pulses to travel between them. As the seafloor shifts, the distances between transponders change. That is how scientists detected the sudden 4-centimeter lurch in just 8 days. The acoustic paths stretched not because of waves or currents, but because the underlying rock slid downslope. Pressure sensors on the seafloor track tiny changes in water depth that can reveal uplift or subsidence linked to this motion. Above the entire system, satellites add a third perspective. Using radar interferometry, INSAR missions orbiting hundreds of kilometers overhead can detect changes in ground elevation on the volcano to within centimeters by comparing radar images taken days or weeks apart. INSAR maps of Etna show broad, slow deformation patterns, including the outward bulging and creeping of the southeastern flank. Where ground-based GPS gives detailed motion at specific points, satellite data fills in the gaps between them, revealing the larger shape of the sliding mass. Seismometers complete the picture. Dozens of instruments pick up even the smallest earthquakes around Etna. Many of these quakes cluster along faults at the base and edges of the sliding flank. They are like tiny squeaks and pops, coming from the underside of a heavy object being pushed across a rough surface. Most are too weak to be felt at the surface, but they show where stress is accumulating and where the rock is failing. By analyzing these patterns over time, seismologists can trace the boundaries of the moving block and identify the zones where the next slip is most likely. All of this data flows into the Volcano Observatory and civil protection offices in near real time. Software constantly checks for anomalies, a jump in downslope velocity on one line of GPS stations, a cluster of quakes along a known fault, a subtle but sudden shift in seafloor distances offshore. When multiple systems show a change in the same area at the same time, it triggers a closer look. Is this just another small adjustment or the beginning of something more serious? From a hazard perspective, there are two intertwined warning systems. The first watches the volcano itself: deformation seismicity, gas emissions, and summit activity. This system is designed to pick up signs of eruptions, lava flows, and explosive events that threaten the flanks and skies around Etna. The second keeps an eye on the flank and the sea sliding rates, offshore motion, and water level changes that might indicate a potential landslide or tsunami source. Coastal tide gauges and offshore pressure sensors are particularly important here because they can detect sudden changes in sea level that might signal a wave in formation. Civil protection agencies use these streams of information to maintain and update hazard scenarios. They run models that ask, what happens if the flank continues to slide at its current rate for decades? What if a moderate offshore earthquake strikes the weakened sediments at the wrong time? What if heavy rainfall saturates the base layers, just as magma intrusion adds extra stress from within? Different combinations produce different outcomes, from minor local damage to rare but devastating collapse scenarios. The uncomfortable truth is that no monitoring network, however dense, can predict the exact timing of a flank failure. The instruments can tell us that the system is moving, that it is sensitive, that some thresholds are being approached. They can narrow down the plausible range of behaviors and provide crucial minutes of warning if a large wave actually begins to form. But they cannot say years in advance, on this day at this hour the flank will break. That gap between what the science can see and what society wants to know is where hard decisions about planning, building, and evacuation have to be made. For most people around Etna, the first signs that something is wrong do not come from scientific papers. They come from the ground under their feet. On the sliding southeastern flank, cracks open in roads and then reappear even after they are patched. Low walls lean downhill. Doors and windows in some houses become harder to close as frames twist slightly out of square. Farmers notice that old stone terraces need rebuilding more often, and that rainwater drains differently than it did a generation ago. These are small things on their own, easy to blame on age or poor construction, but taken together they trace the slow march of the mountain toward the sea. Along the coast, the stakes are higher. Towns like Asiriale Riposto and Giardini Naxos sit on low ground facing the Ionian Sea. They rely on harbors, beaches, and seafront roads that would be among the first places hit by any wave raised by a flank collapse. For now, life there looks normal. Cafes open onto promenades, fishing boats rock gently in the harbors, children play on black sand shaped by old lava flows. Yet, when civil protection officials lay their hazard maps over these same streets, entire neighborhoods fall into zones labeled for tsunami risk. Signs in some areas already mark evacuation routes and safe assembly points on higher ground. Even without a major collapse, the sliding flank has real economic consequences. Authorities must constantly repair roads, pipelines, and retaining walls that are strained by ground movement. Some infrastructure projects are delayed or redesigned because surveys show that the land beneath them is not stable over the long term. Builders and planners face hard choices about where to allow new housing and where to say no, knowing that every new structure adds people and value to a slope that is already in motion. Insurance companies quietly adjust premiums and exclusions in the highest risk areas, reflecting a danger that most policyholders never see directly. In response, Italy's civil protection system and local governments have been forced to treat Etna as more than just an erupting volcano. Emergency plans now include scenarios where the main threat is not ash or lava, but waves generated by a flank failure. Coastal towns conduct drills in which sirens sound, and residents practice moving inland and uphill in minutes. Schools teach children to recognize the signs of a possible tsunami, such as rapid withdrawal of the sea or strong, unusual shaking. Hospitals and critical facilities review backup plans for evacuation if necessary. These exercises are disruptive and sometimes unpopular, but they are one of the few ways to turn abstract models into muscle memory. For scientists and emergency managers, communication may be the most delicate part of the response. They must explain that the flank is sliding, that a past collapse likely launched a tsunami, and that future failures are possible without claiming to know exactly when or how large any event will be. If they speak too calmly, people may ignore evacuation maps and drills. If they speak too dramatically, they risk panic, economic damage, and the erosion of trust when catastrophe does not arrive on cue. In public meetings, you can hear the tension between these extremes. Residents ask whether they should move now. Officials answer with probabilities, timeframes, and layers of precaution. Despite all this preparation, everyone involved knows there are limits. No network of instruments can provide years of advance notice for a sudden break along the sliding surface. At best, it can offer a clearer picture of the risk and a narrow window of early warning if motion accelerates rapidly. The rest depends on decisions made today: where to build, how to reinforce, how seriously to take a danger that creeps forward in centimeters per year, but could in the worst case make its presence known in a single violent hour. Inside the observatories that watch Etna, the graphs and maps of flank motion are more than lines on a screen. They are the starting point of a difficult argument. How dangerous is this slow slide really, and what should be done about it? One school of thought looks at the decades of data and sees a system that, although unstable, may remain in a state of creeping equilibrium for a very long time. In their view, the weak sediments beneath Etna's southeastern flank act like a thick, sticky brake. They allow the mountain to move, but they also dissipate energy as heat and friction. The sudden 4-centimeter lurch offshore was alarming, they admit, but it did not trigger a chain reaction or noticeable damage on land. To these scientists, the more likely future involves continued slow sliding, occasional small jumps, and perhaps limited local failures. Serious enough to demand monitoring and planning, but not necessarily a single catastrophic collapse. Others are less reassured. They focus on the fact that the same weak horizon which allows slow motion also provides a continuous slip surface under an enormous mass of rock. In this interpretation, the current creep is not a sign of safety, but of a system already very close to failure. The 4-centimeter shift offshore is not just a curiosity. It is proof that the flank can move abruptly along that surface without help from an eruption or a major earthquake. Add the evidence of a past massive collapse carved into the Valle del Bove and the seafloor, and they argue that treating the present motion as harmless would be dangerously naive. Complicating the debate is uncertainty in the models. Computer simulations of flank collapse and tsunami generation depend on many assumptions. How thick the sliding block really is, how strong or weak the sediments are at different depths, whether failure would occur in one piece or in stages. Change those parameters and the predicted waves at the coast can shrink from tens of meters to only a few, or vice versa. Some researchers urge caution in public communication, stressing that worst-case scenarios are just that, worst cases. Others counter that emergency planning has to consider those extremes precisely because their consequences would be so severe, even if their probability is low. There is also a philosophical divide about how much weight to give the most recent measurements. Should the 8-day 4-centimeter slip be treated as a rare outlier, a once-in-decades twitch, or is it part of a pattern that will repeat more often as the system evolves? Long-time series show periods where the flank moves faster after heavy rainfall, after certain eruptions, or after regional earthquakes. But the exact combination of triggers that would push it from faster creep to runaway failure remains unknown. Some scientists argue that until that threshold is better understood, it is safer to assume the system is closer to it than the opposite. Beyond the scientific arguments, there is a quieter but equally intense discussion about responsibility. Urban planners and politicians ask volcanologists for clear answers. Is it safe to approve a new housing development here? Should we relocate critical infrastructure there? Scientists working with probabilities and error bars cannot give absolute guarantees. They can say that risk is higher in some zones than others, that certain slopes have a history of faster movement, that models predict particular stretches of coast would be hardest hit by a wave. But they cannot promise that a collapse will or will not happen within a human lifetime. That gap between what science can say and what society wants to hear is where frustration often builds. For residents, the debate can feel distant and abstract, yet its consequences are very concrete. If authorities emphasize the most alarming possibilities, property values may fall, investment may dry up, and young families may choose to leave. If they downplay the danger, people may be caught unprepared if the flank does fail. Some locals choose to trust the monitoring networks and carry on confident that any serious change will be detected in time. Others feel that they are living under a slow-moving threat that no one is willing to name plainly. Social media and sensational headlines can swing opinion between complacency and fear in a single news cycle. In the end, everyone involved, scientists, officials, and the people who live on these slopes and shores, is trying to navigate the same uncomfortable truth. Etna's southeastern flank is both stable enough to live on today and unstable enough to pose a real, if uncertain, risk for tomorrow. The data is clear that the mountain is slipping. The debate is about how fast, how far, and what that demands of us now, before gravity writes the next chapter more decisively than any model. On a clear day, it is hard to look at Mount Etna and imagine it as anything other than permanent. The mountain rises above the haze with the same outline it has carried for generations. Tourists pose for photos. Fishermen glance up from their boats. Children draw it as a simple triangle on school worksheets. Nothing in that familiar shape hints that one side of this volcano is quietly slipping toward the sea. Yet the instruments and scars in the landscape say exactly that. The southeastern flank is moving not in meters per second, but in centimeters per year, and gravity never gets tired. What makes this especially unsettling is the double nature of the threat. On most days, Etna behaves like a normal active volcano. Lava flows, ash plumes, minor explosions. These are hazards we can see coming, track with satellites and cameras, and often avoid with timely evacuations. The sliding flank is different. It is a structural weakness built into the foundation of the volcano itself. It does not need an eruption to act. It only needs time weight and the wrong combination of triggers to find its breaking point. Does that mean a catastrophic collapse and tsunami are inevitable in our lifetimes? No one can say that honestly. The system may continue to creep for centuries, broken only by small failures and local damage. But the existence of a past giant collapse, the clear evidence of an active sliding surface, and the recent silent offshore lurch all tell us that the possibility is real. That should be enough to shape decisions now while the horizon is calm and sirens are silent. Preparation in this context is less about predicting a specific day and more about reducing the cost of surprise. It means avoiding new construction in the most mobile zones, reinforcing critical infrastructure, maintaining dense monitoring networks, and making sure that coastal communities can move quickly to higher ground if the sea ever behaves strangely. It means teaching children that the beautiful mountain on their drawings is also a machine that changes shape, and that respecting it includes knowing how to leave its path when necessary. Standing on Etna's slopes or walking along the Ionian shore, it is tempting to trust what your eyes see, a coastline that has always been there, a volcano that always seems to recover from its eruptions. The deeper truth lies in slow numbers scrolling across scientists' screens in millimeters of motion that add up over years in the quiet memory of a mountain that has already fallen once. Whether the next chapter in that story arrives in restless centimeters or in a single violent hour will depend on forces we cannot fully control. What we can control is how seriously we take the warning written right now in the subtle but relentless slide of rock toward the sea. If you've stayed with us to the end, you've just seen a side of Mount Etna that most people never think about. Not the fire at the summit, but the slow, silent slide of an entire flank toward the sea. That new fracture on the mountain is more than a crack in rock. It's a reminder that this volcano is still rewriting its own shape. Tell us what you think in the comments. Does Etna's moving flank feel like a distant curiosity or a real warning for the future of these coasts? If this video gave you a new way of looking at the mountain, please like it, share it with someone who lives near a volcano or the sea, and subscribe so you don't miss our next deep dive into Earth's most dangerous places.